Hi everyone, my name is Antonio Collesei. I'm a PhD student at the third year at the University of Padova, and I'm going to present our latest work, which is ALLSTAR, a computational tool able to infer reliable causal rules between somatic mutations and cancer phenotypes. This work has been carried out in collaboration with the Veneto Institute of Oncology, the Department of Medicine and Oncology at the University of Padova, and the Department of Information Engineering, as well at the University of Padova. ALLSTAR, straight from the title, works with causality. But what is causality? I can already tell you what is not, and correlation is not causality, is not causation. And is an axiom that you may find in every Statistics 101 course, and that works pretty well until you have to define what is causality. Getting more mathematic, two entities that go well together are correlated, but that doesn't mean that they are actually related, that one determines the other. For example, in this case, Nicolas Cage is not really related to people getting drowned, so he's not really making people drown in a pool. The first one gave us a mathematical definition of causality, was Pearl. Imagine that you have a treatment, a medicine, and you want to measure what is the effect of giving this treatment to a person. You have to get the information of the outcome of giving this treatment and the outcome of not giving the treatment. And you have to get the difference between these two quantities, but this actually is not measurable because you cannot force one person to get the treatment and the same person not to get the treatment at the same time. So you have to calculate the average treatment effect with a cohort of more patients. And this is measurable because you can count the expectation of this difference. And assuming that there is independence and randomization in the treatments, you can get this simple result. But this is not the case in every situation because this can be estimated only for randomized controlled trials. In real-life observational studies, you don't get that, and because there is a group of confounders that may influence the effect that the treatment has on the outcome. Let's see it with an example. Imagine that lots of people that go to bed with the shoes on wake up with a headache. You may think that the shoes are actually causing the headache, but it's not really that way if you add the confounding effect of drinking the night before. And you may understand that in this way, it's the drinking that causes you to wear the shoes on while going to bed and then waking up with a headache. And it's the drinking the root cause. So you have to count for that and mitigate the effect of the treatment based on the confounder. So we can measure this effect if we count the average treatment effect blindly without taking into account a confounder. This is what we get. We may get an effect of 0.33. I made this example really suited for giving you the idea that the situation can be reversed. And in fact, it is like that if we have this situation in which most of the people that are going to bed with the shoes on are actually drunk. So if we do the same, but accounting for the stratification given by the confounders, we get an effect that is negative. So the situation is opposite with respect to before. But the situation is it's not like that every time. You don't have one confounder and one treatment. You can have multiple confounders, multiple treatments, and you want to evaluate in a complex world what is the combination of this stuff that is giving the highest effect. So it makes sense to work with rules. A rule is something like that. You get combinations of treatments, you get a specific outcome you want to evaluate, and you get a set of confounders. And with the rule effect, that it is measurable based on this formula, that I'm not going into detail, you can actually get the rules that have the highest causal effect with guarantees on the result. Because in fact, we borrowed the reliable estimator of the effect from Budatoki et al. And we developed with that a branch and bound algorithm for the discovery task, but with statistical guarantees that were not actually present in the state of the art. In fact, we want to bound the family-wise error rate, which is the probability of returning at least one false positive in a series of hypothesis tests. You may understand immediately that for a number of tests that is like super high, the family-wise error rate goes straight to 1. And we want to avoid that. So we apply Bonferroni correction, which is super conservative and simple way to do that. And we bound the family-wise error rate, so to make it stay low even with a super high number of tests. We also managed to reduce the number of tests with a biologically informed network. In fact, in order to create the rules with the right combinations of stuff, of genes that are biologically meaningful, we took a protein-protein interaction network from Reactome, and so we built the rules in a functional way. Our contributions are guarantees for multiple hypothesis testing, the exploitation of biologically informed network with PPI. We also proved that the general problem is NP-hard, but I'm not going into detail because you can find it in the paper. And we experimented on breast cancer data. So we took data from Cancer Genome Atlas, which is a big repository on cancer, not only breast cancer, but pan-cancer as well. We took confounders, which can be age, sex, race, medical history, and so on. And we got as treatments somatic alterations, as well as loss of heterozygosity, hypermethylation, and so on. And the outcome that we want to evaluate is cancer subtypes, histological or molecular cancer subtypes. So the idea is getting rules like that, in which you have combinations of genes that determine causally a certain subtype, given a certain confounder or a set of confounders. And ALLSTAR reports only statistically meaningful results, so positive effects. And you get results like this, in which you have a set of rules. These one are the top ones, in which hopefully you get stuff that is already reported in literature, and as you can see, most of it is, and other stuff which is not really present in literature, but they just make sense, they are sound. Let's see, for example, this one, in which you have these two genes, MST1 and ERBB2, which they just make sense. I mean, MST1 alterations are consistently determining basal subtype, and this exists in literature. And ERBB2 actually is more related to overexpression and transcriptome alterations rather than actually somatic alterations. But it can be studied more. So another one is RHOA, which has an important anti-metastatic role, and the combinations of these two genes, they just make sense. They can be new potential targets for evaluating this complicated disease, which is breast cancer. Another motivating example is the fact that we got results from really meaningful genes like TP53 and CDH1, which are also frequently mutated. And we didn't get results from TTN and HMCN1, which are as well super frequently mutated, but they are also super big in size. So this means that they harbor lots of mutations, but they are not really related to the disease. And so they constitute some kind of evident false positive that we didn't get in our analysis, so it's good. As a plus, we did a pathway enrichment analysis with a list of rules that we got as a result. We extracted the list of genes from these rules, and we did a pathway enrichment analysis on that, and we got a list of significantly enriched pathways with David, which is like the most common pathway enrichment tool available online. So we got obviously breast cancer, but also other important and really related pathways to breast cancer. And so the results are really motivating in that sense. Take-home messages, I will just sum up what we just said. So ALLSTAR identifies causal relations between alterations and cancer phenotypes. The algorithm is biologically informed. It is robust statistically to false positives, and it recognizes stuff that exists in literature as well as some more potential new targets that may be studied in future. So I will end my presentation with this motivating quote from Julia Pearl. In the book of Why, he said, "To build truly intelligent machines, teach them cause and effect." So this is really motivating to study this topic, and also for the future, but as well for the present, in which we are witnessing a revolution in machine learning and artificial intelligence. Thank you for your attention, and see you in Lyon or somewhere else. Thank you.